Hello everybody, let's talk about section 4.4, which gets into properties of logarithms and takes our discussion a little bit further than we had about what these logarithms are all about and how they can help us. So in this section, what you're going to be asked to do is, of course, evaluate logarithms. We're going to apply something called a change of base theorem. So we should be able to rewrite logarithmic expressions, of course, using this change of base theorem, as well as using several properties that we'll go over to expand logarithmic expressions using these properties of logarithms and compress these logarithmic expressions into single expression. And in addition, we will talk about a few applications as well at the end. So let's get into this discussion about what the change of base formula says. Here's the change of base formula. It says let A and B be bases where A and B is greater than 0 and A or B are not equal to 1. Our normal definition of the logarithm, recall, said that we had to have a base that was positive and not equal to 1, so this fulfills all of those properties. This rule says if we have a logarithm base A of x and we want to evaluate it at a different base, B, then rewrite it by saying the logarithm base B of x, but then divide by the logarithm base B of A. And you might be scratching your head at this point saying, well, what's the point of all of this? Well, the point is that most calculators do not have the capability of evaluating an expression like this one. This one says, let's take the logarithm base 2 of 3. In other words, we would be asking, well, to what power must I raise the base 2 in order to get the result 3? Well, clearly 3 is not one of 2's even exponent values, so how do we actually evaluate this? Well, our change of base theorem provides us an answer. It says, in essence, that if we don't like the base that we're dealing with, rewrite it in terms of another base. So, for example, I might be interested in rewriting this using the change of base theorem to rewrite it as a common logarithm. So this would say, all right, the logarithm base 2 of 3 by the change of base theorem would be the same thing as the common logarithm of 3 divided by the common logarithm of 2. That's it, right? So what we would do right here is we would rewrite this, and if I were to actually evaluate this, and I broke out my calculator to check this out, I found that the logarithm of 3 was about equal to 0.47712, and that the common logarithm of 2 was approximately equal to 0.3013, 103 when I rounded. And when I worked that out, that gave me about 1.5851, which in an odd way, this is actually rounded. I'll write approximately right here because we don't actually get a nice round number with this. We get a near rational value. We could have chosen a different base altogether, and to verify this, you should do this on your calculator. Verify that if you take the natural logarithm of 3 this time and divide it by the natural logarithm of 2, that you also get this value. The point is, it doesn't matter which base we change it to, that logarithm allows us to rewrite the expression in such a way that we are able to evaluate it using something in our toolbox rather than out of our toolbox. So this allows us to actually evaluate logarithms like this. That's pretty cool. Well, what other tricks can we do with it? Well, let me show you another trick up here, up at the top, and we'll get to this stuff down at the bottom in a minute. Let's concentrate on this. Let's say we're told to evaluate an expression like this one. Logarithm base 4 of 7 times logarithm base 7 of 5 times the logarithm base 5 of 16. Well, by the change of base theorem, we can actually rewrite each of these logarithms and see if there's anything that we can do that might be useful for us. And so if I were to rewrite this, let's use the change of base theorem. I'm going to rewrite each of these as natural logarithms. Logarithms base e. So what do I have? I have the logarithm base 4 of 7. So if I want to change that into a different base, say our natural logarithm, I could rewrite it by the change of base theorem as the natural log of 7 divided by the natural log of 4. And same thing with each of our expressions. So I could take the natural log of 5 and divide it by the natural log of 7, and take the natural log of 16 and divide it by the natural log of 5. And now let's see what's happened right here. It looks like we've actually come up with a couple of like factors, like terms, right? Or like factors that can be canceled in the numerator and denominator of each of these expressions. And so that's what I'll do. I'm going to cancel this natural log of 7 with this natural log of 7. And I'm going to cancel the natural log of 5 with the natural log of 5. And looking at what this means, I've got 1 divided by the natural log of 4 times the natural log of 16 over 1. And by our multiplication rules for logarithms, or for fractions, pardon me, I'm going to have the natural log of 16 divided by the natural log of 4. And you might be thinking to yourself, okay, so I'll just get my calculator out and I'll evaluate the logarithm of 16 and divide it by the logarithm of 4. But it turns out that on the basis of my change of base theorem, if I go in reverse right here, I really actually have here a logarithm base 4 of 16. And this question asks, to what power must I raise the base 4 to get 16? Answer, 2. And you can, again, verify this in your calculator that that is the case. But, well, it's the case. Okay, more to come.